Hello, everyone, and welcome to this edition of 30 Mechanical Minutes, virtual content for real-time professionals. My name is Doug Picklick. I'm the editor of HPAC Magazine, the industry magazine that has been informing the plumbing and HVAC and mechanical industry in Canada since 1925. Yes, it's been 100 years of serving the industry in Canada for HPAC. Today, we're here talking about hydronic systems and the concept of thermal storage. And I'm joined once again by longtime HPAC Magazine contributing writer and hydronics industry expert, John Siegenthaler. Hi, John.
Hi, Doug. Hi, everyone. Good to be here.
Great to see you once again. Before we begin, I'd like to thank our sponsor for this edition of 30 Mechanical Minutes, and that is Lochinvar, manufacturer of high-efficiency water heating and storage products, along with Aquatech Sales and Marketing, the manufacturer's representative for Lochinvar products across most of Canada. Let's just be clear about what we're talking about today, and it's hydronics and thermal storage. First off, John, when I hear thermal storage, I picture large insulated tanks full of hot water. So is that what we're talking about here when we talk thermal storage?
Well, that's one of several ways to do it, and it's probably the most common way. It's been around for decades. Thermal storage has been used, for example, biomass boilers, pellet boilers definitely count on it. It's been used with solar thermal systems again, for decades. The idea that you have some kind of a heat source that may not have a scheduled heat output, solar collectors being a good example. So we grab the energy when we can or when it's lowest in cost, and we put it into storage, and then we extract it when we need it.
Right. So it's this idea of what we call a storage as a battery. Is that
Hmm.
it? So because
Yeah, you can think of an insulated tank as a thermal battery versus an electric battery. You can store heated water, you can store chill water. Some systems that we were chatting earlier even store ice and use that ice for cooling.
yeah. Okay. Well, in the again, when I think of a battery, I tend to think of electrical, like the
Hmm.
battery in a watch or the battery in our car, something like that.
Hmm.
But for the HVAC industry, I know when it comes to electricity storage, there's a lot of talk of electrification within the hydronics industry. Air to
Hmm.
water heat pumps certainly
Hmm.
becoming very common. Water to water's been around for a while as well. So this electrification. Um, and then, of course, when it comes to electrification, electrical utilities are introducing these time of use rates so we can make electricity, we can gather electricity when it's at its least
Yeah.
expensive. And this is
Hmm.
trying to be more efficient with our use of hydronics.
Yeah, off-peak rates, both in the US and Canada. I feel, we have rate structures now from some utilities. I think we're going to see more and more of it because it's a what a utility would call a demand side management tool, a way to encourage when that energy has to come off of that grid. And by encouraging it using financial incentives, pricing on the electricity, you can basically get customers to buy it when the utility grid is less loaded, and not buy it when the utility grid is being heavily loaded, like a hot June afternoon.
Yes, much like today. So,
Right.
in your article in our recent June issue of HPAC, you mentioned how modern hydronics can serve as what you called the glue that can bind together the use of heat pumps, this time of use electricity rates, and thermal storage. This is where that
Hmm.
comes in to create some real market opportunities. Um,
Absolutely. Yeah.
so,
Yeah. Hydronics, of course, hydronics has been around since the late 1800s. We've used boilers, we've used solar collectors, biomass boilers. We've used all kinds of different heat sources. And really, one of the unique characteristics of hydronics versus forced air is very, very high thermal storage potential of water. A given volume of water can hold almost 3,500 times as much heat as the same volume of air with the same temperature change. So it's a natural extension of hydronic heating to bring thermal storage into the picture when economics are justifiable to do that. And with rate structures that, for example, we're dealing with a rate structure now in one utility where the on-peak cost of electricity is about 44 cents a kilowatt hour, and the off-peak rate is 7 cents a kilowatt hour.
Yeah.
So that's a huge, it's almost a 7-to-1 rate differential. And I use as an example, imagine in the States here, gasoline locally is selling for about $3.30 a gallon US. Imagine you could go to the gas station at 2 o'clock in the morning and buy that gasoline for 55 cents a gallon. So do you think there'd be a line at the gas station, Doug?
Yeah. Yeah. No, 100%. So yeah, and then that's the incentive to drive people to use the energy at those times of days. And this
Right.
is one method for doing that. Gathering, using electricity, store heat or store cooling
Hmm.
when it's most cost effective, cost
Yep.
efficient. Okay. And to do this, this is where again the thermal storage comes in. And again, we were talking about tanks of water as your
Hmm.
kind of that's what you talked about in June. So maybe we could show kind of a basic setup
Yeah.
that you talked
Yeah.
about in the June issue, and we can.
Yeah, we can go right to that slide and I'll walk you through it. Again, this is the June issue of HPAC, and I'd encourage you to look at that on the website because we don't really have time to go into great depth on the different modes of operation, but that schematic that you're looking at is based on an air to water heat pump, a monoblock heat pump. And then you'll see the red lines represent the, in this case, hot mixture of antifreeze and water coming in. And the valving and the circulators that are there can all be controlled. And essentially, we can take that hot water coming in, we can send it directly to the load. And over on the far right of the schematic, you'll see I'm showing panel radiators on what we'll call a home run distribution system with a variable speed circulator, very simple, scalable system. Excellent for low water temperatures. The panel radiators can be sized to operate in the range of 110, 120 degree Fahrenheit water. But you also see the tank down at the bottom. So at at times when the cost of electricity is low, and typically these are night times or weekends or major holidays when the load on the utility grids are low, what we would do is would close a valve just to the upper left of that hydraulic separator. It's labeled MV1. And the circulator that pumps the fluid through the heat pump would actually send that hot heated fluid down into the top of that thermal storage tank. Cool water would come out the bottom. You'll see another valve that's labeled MV2. That valve would open. So that's the flow path now between the heat pump and thermal storage. So we'd call that the charging mode. And then there is another mode where the heat pump would be off and we would turn on circulator P2. We'd actually control the speed of circulator P2 and we'd be sending cool water coming back from the panel radiators into the lower portion of the tank. Hot water comes out the top, goes over through MV1, that valve, goes through the hydraulic separator and out to the load. So there's basically three modes. There's heat pump direct to the heat emitters, there's heat pump to storage, and then there's storage to the load. And that can all be controlled, depending on what the rate structures are. Down in the very lower left, I'm showing how you could extend the amount of thermal storage with, in this case, 3 tanks. Those tanks are piped in series with each other, and there's a very specific reason for that. We're trying to maintain good temperature stratification. We want the hottest water in the top of the rightmost tank, the coolest water in the lower left tank. So again, I'd encourage you to go back to the June issue, take a good look at this system, and it walks you through these different operating modes.
You brought up that concept of stratification in the article. We didn't go too
Mhm.
deep into it, but even for a single tank, you talk about the importance of keeping it stratified, not
Correct. Yep.
a
Yeah,
consistent temperature.
we don't want to mix the water, and that's why you see the blue at the bottom, the red up at the top. And if you follow through the charging mode versus the discharging mode of that tank, uh, both modes are going to help preserve the stratification. You also see that the pipes come in horizontally instead of vertically. And down in the lower right, it's a little hard to see it there at that scale, but one of the systems we've been working on, and we're going to get to that in just a minute, we're using what are called sparge tubes inside the tank. And these are basically internal headers that have holes drilled in them. So as the flow comes into the tank, the flow is introduced slowly and gently into the tank in the right direction to minimize any disruption, any kind of mixing currents inside the tank. And again, the reason for maintaining stratification, there's a thermodynamic advantage in doing that. Essentially, we have greater usability of the energy in the tank when we preserve stratification versus mixing the tank.
So this is well, a project that you're, again, you referred to it here as a research project. So this is
Mhm.
very much in a concept.
It is, yeah. This is being funded. This is up in Millinocket, Maine, which is a pretty cold place. You can see a winter photo there, almost 8,800 degree days, -9 Fahrenheit design temperature. The project is being sponsored through Efficiency Maine, and basically it's a proof of concept. And the proof of concept is that with off-peak rate structures, we can use very low cost, very low operating cost systems without ever losing comfort in the building. We are not sacrificing comfort in these buildings. And I'm working along with Ridgeline Analytics, GridWorks Consulting, and there's actually several systems up there. And we can jump to another slide quick. And these are a couple of the houses where these systems are installed. These are not exceptional houses from an energy standpoint. These are houses built probably in the 50s or the 60s. There's reasonable insulation, but nowhere's near what current code standards are. So this is not the idea that, yes, this works in something like a passive house or an R2000 house, but it can't work in an average house. And that was by choice. We wanted to show that average houses could be retrofit with this strategy. If we jump to the next slide, yeah, well, there's a photo of some of the hardware involved. Over on the far right, you see those three tanks lined up. Those are the three thermal storage tanks that are piped up in series. They
Okay.
do have electric elements in them. Those elements are not being used right now, but they could be. They could be used to grab low cost energy if and when the cost optimization strategy says, yes, we should grab more than what the heat pump can produce.
Okay.
We can jump to one more slide.
Yeah.
Yeah, these systems are using a kind of a unique air to water configuration. I call it a cascading system. Basically, the outdoor unit you see on the left there, that's a standard outdoor condenser unit running on R410A. And that has a refrigerant line set that goes inside and it goes to a box. You can see it in the middle photo there. Um, that's actually another heat pump. So there are two complete heat pump cycles involved here. The first one lifts the outdoor temperature to an intermediate temperature. And then that refrigerant goes in and serves the evaporator of the indoor unit. And we've actually seen these things operate over 180 degree water temperature, 180 degree Fahrenheit water temperatures. Um, these were developed primarily for domestic water heating applications, and they were selected in some of these early research projects because of this high temperature potential.
Yeah.
There are other technologies coming, carbon dioxide as a refrigerant and propane as a refrigerant that are both capable of producing relatively high temperatures compared to what we're working with either an R410 unit or an R32 unit. So let's go to next slide.
Okay.
One of the things that the researchers, one of the premises of this whole thing is that as we add more and more large scale renewable electrical generation to grids, the problem is not so much the lack of energy generation, it's as it says, the inability to fully utilize peak output. there
Right.
are times when certain utilities, and these are utilities that typically have a lot of solar, for example, California, a large scale solar implementation, or in places like Minnesota, Maine, large wind farms. And in some of these utilities, there are times when the generation actually exceeds the load on that grid. And rather than try to curtail generation, in other words, shut off your solar panels or shut off your wind generator, utilities want to sell that power at a wholesale rate to other utilities.
Right.
And they encourage that sale by changing their price structure. And they actually put out a 48-hour advanced pricing structure. So right now, we could look at what are the wholesale electric rates for the next 48 hours. And those rates are all based on projections in load, projections in weather. And utilities have, they have lots of data in order to use smart algorithms, artificial intelligence to say these are what the price structure should be. And there's actually times when the price structure at the wholesale level can be negative. And I couldn't believe that when I first heard it, but I've seen since ample evidence of that. The utilities are actually looking to unload that power from the grid rather than to curtail its generation. So
So,
imagine,
so yeah, just a sec. So this is like, so instead of the time of use, like timing, this is more when there's the most generation. So it could be in the middle of the day when there's tons of sunlight and a really windy day.
correct.
All of these renewable sources of energy are providing so much power that
Yep.
the cost is coming down.
Yeah, and some utilities are already at the point where there's so much renewable generation on their system that they have to look at ways to unload some of that. And this is where, there's a great opportunity, especially if these wholesale rate structures and the 48-hour advanced forecasting. And that's what you'll see point number 3 on the slide. It says forward-looking optimization. This is where we're using a computer and using a pretty sophisticated algorithm to say, if we know what the next 48-hour pricing is on an hour by hour basis, what is our best operating mode right now? Should we run the heat pump? Should we draw from thermal storage? And so forth. And of course, that's a dynamic situation. So calculations are always being done. What should we do next?
Right.
And yeah, there's the research system. Now, again, we don't have time to really delve into it, but the basic elements that are in that June HPAC article are here. There's actually extra equipment shown on this schematic. There's flow meters, there's temperature readouts, there's more instrumentation involved. You'll see there's an existing oil-fired boiler. This is in one of these houses. That existing oil-fired boiler was kept in as part of the system because if the heat pump goes down or if the control situation, remember, this is a research project. This is not being intended as ready for commercialization immediately, but I feel there's a very good chance we will get there with commercialization once the concept is proven. But in any case, that boiler is there as backup. And for example, the control algorithm uses the internet to get price structure. What happens if the internet connection goes down? Well, the system automatically reverts to either just operating the heat pump or operating the boiler. So the people that have put these projects together have been very conservative in the sense that, if the internet goes down, the house is still going to have heat. So where are we going from here? Well, this is the next variation on this. This is a project that'll be installed this summer. Again, it's going to be up in that northern Maine location. We're going to actually be using a prototype R290. That's a propane-based air-to-water heat pump. And we can get temperatures up around 75 C. I think that's just under, it's about 167 degrees Fahrenheit. And over on the right, you'll see some of the same elements. You see the thermal storage tank, you'll see the existing boiler. The distribution system in the house that this system is planned for actually has cast iron radiators,
Yeah.
and there's 4 zones. And then you'll see a couple other details that are kind of floating there. One is an air handler that could be used for cooling in the summer. Millinocket really doesn't need a lot of cooling, but again, looking forward towards eventual commercialization of a concept, a lot of North America does want cooling. So I feel very important that the system be designed so cooling could be added. And then the other option is adding domestic hot water. And there's multiple ways to do it, but the detail you see over on the lower right, that brace plate heat exchanger, the circulator, the flow switch, that could actually just slide to the left, connect between where the two A's are and where the two B's are on that tank. And that tank now becomes the thermal mass that would transfer heat through the stainless steel heat exchanger to the domestic hot water. We're not at the point where we're putting that cooling and that domestic water onto the system. We will get there. So this is a system that ultimately can bring thermal storage in, do space heating, domestic water heating, and hydronic-based cooling.
Okay, we've got a lot of questions coming in, and this is great.
Okay.
I did want to ask, I mean, so we did address a little bit domestic hot water and potential cooling demands as well. Now, we're talking just about insulated storage tanks using water or a
Mm-hmm.
glycol water mix, depending on how you set up the system, if there's a heat exchanger or not.
Mm-hmm.
Um, but you can share, there are alternative methods,
Yep.
thermal storage technologies out there. I know I had the opportunity to go to ISH this summer and I saw the UK-based Sunamp folks and their
Mm-hmm.
phase
Yep.
change material in a
Yep.
smaller box, kind of um, I guess it could be modular, but it's a nice compact size for situations really in Europe. It makes a lot of sense. Um, and then there's other solutions as well. I know that the Steffes product using bricks, right, to
Mm-hmm.
thermal
Yep.
storage as in a different method.
Yep.
So can you
Yep.
just talk
Solid base thermal storage.
solid base? Yeah.
Yeah, and it not necessarily just the bricks, although the bricks are used primarily with electric elements. They're fairly dense as far as heat storage, and they can handle the high temperatures. But imagine, for example, some type of a solid material installed under a slab in a building. Probably something like the technical term is flowable fill. It's a very low strength concrete. It's basically a mixture of some Portland cement and sand. And then you would have embedded tubing grids in that. And you could have a fairly large volume, which means you can store at a relatively low temperature. And that has definite advantages. Remember, storing the number of BTUs you store isn't just based on temperature, it's also based on the heat capacity of the material you're storing it in, whether it's water or a phase change material or a solid material. So yeah, the phase change materials are starting to get a market in the US. They're primarily developed around, and you kind of hit it, Doug, the small size. They're definitely smaller than water tanks. And they're primarily being aimed at domestic water heating, where especially in, you mentioned the European market, flats or apartments where space is very limited. You would not have space to put even one of these thermal storage tanks in. So phase change materials are out there, and they're starting to get some traction in North American market. And again, all these materials can play well with hydronic-based heat generation and hydronic-based heat distribution within the building.
Yeah. Okay. Well, we're going to jump right to some Q&A here. I see we've
Mhm.
got a good over a dozen questions here. Does the concept of hydronics precede HPAC magazine? Well, yeah, I think, John, you said it does. There's hydronics been around a long time.
A little bit, not by much though, at 100
Not by
years.
much,
Yeah,
but I
late
know,
1800s,
and it was
late
all gravity,
1800s.
right? It was
It
gravity
was all
powered.
gravity based, no circulators, no
No,
electricity,
no
cast iron.
pumps.
Yeah, and it
Yeah.
worked. And I've always been in awe of the engineers that used those principles back then. I mean, today, we pick a circulator, we put it in, and we can push water pretty much any way we want it. Back then, that was not the case. They had to rely strictly on the buoyancy effects of hot water versus cold water. But yeah, so hydronics, 130, 140 years, something like that.
Okay. In North America, have you seen systems
Yeah.
in North America using gravity? Yeah.
Oh yeah.
Oh
Oh
yeah.
yeah.
Okay.
Yeah. But yeah, circulators really developed in the 1930s. So almost
Okay.
anything prior to that was a gravity-based system.
There we go. Thank you so much for that
Hmm.
education, and thank you, anonymous attendee, for asking that question. That first schematic that you used, John,
Hmm.
there was no heat exchanger in there, so that's all. The whole system's using glycol.
That would be, or an alternative. It could work on water. That's a very interesting kind of side topic. There, air to water heat pumps in the European market. There are thousands of heat pumps that are air to water that are running on water without any antifreeze, and they do use freeze protection valves. These are thermostatic valves that would open and drain water from the heat pump during a power failure. And I'm going to throw another bone out there that at some point we will address in HPAC. I'm
Yes.
just going to call it pneumatic based freeze protection. And I won't share the details yet, but the
Okay.
word pneumatic will mean something to many people here. So
Okay. Well, I look forward to learning more about
stay,
that.
stay tuned. But
Okay.
and bottom line is if you can get the water out of the heat pump before it freezes, you don't have to use antifreeze.
Right.
If you can't, you definitely do want to use antifreeze. So, all these systems, whether they're antifreeze based or not, and to the question that was asked, yes, that first system would use a mixture, probably a 30% solution of propylene glycol and water
Yeah.
throughout the system. The downside of doing that, of course, if we have a very large storage volume, is you get a lot of antifreeze, and it gets
Yeah.
expensive from just this. You could have $2,000 or $3,000 worth of antifreeze in a big system.
Right.
So there's a lot of incentive to look at either a heat exchanger that would separate the heat pump from the water-based portion of the system, or some type of freeze protection system other than using antifreeze.
Okay. Someone asked, and again, I think we're referring back to that first image. Why is there a differential pressure bypass?
Ah,
Wouldn't it be
very
worth it to
observant.
put a smart circulator instead?
Okay, now I'm going to tell you to read the article in June HPAC, and it explains
Okay.
why it's there, but I'll give you a quick summary. It's there because when the heat pump first turns on, the circulator turns on first and will run for 2 to 3 minutes before the compressor starts. This is common startup on many air to water. And that differential bypass valve is in there to actually allow that water to recirculate when it comes out of the heat pump. The valve MV1 is going to be closed. The water is simply going to go over. It can't go through MV1. It's got to go through the differential bypass and right back into the heat pump. It's there to bring that water up to temperature before it releases it to the balance of the system. And that's important to maintain stratification.
Jeff is asking, how do you size the tank? Um, and again, you could use multiple tanks if you're looking to store even more heat, but
You can. Um, Jeff, it's again, it's a complicated answer. The best way to get a handle on it, this is not the easy way, but it's the best way, is to have software that will literally simulate the operation of the system hour by hour, minute by minute, based on what the rates are, when the off-peak rates occur, what the house load is, and so forth. Um, the systems we've been working with were designed to get the house through a design day with 5 to 6 hour periods where there's no input from the heat pump whatsoever. So imagine, again, -5 degree Fahrenheit overnight temperature, 5 to 6 hours with no heat pump operation. You look at the volume of the tank, you look at the temperature drop that it can go through and still maintain comfort in the building. This will be, quite honestly, these kind of systems eventually will be designed by computer simulation. We can put
right.
another tank in, we can run the scenario, and we can quickly see, is it economically justified to do it? But
Yeah.
the three tanks are proving good. One of the slides I didn't have time to really get into, we can show that under these very cold winter nights, that heat pump can be off for 5 to 6 hours and there's no drop in comfort in the house.
And these are insulated tanks.
They
Uh,
are.
in all cases, are you insulating all the piping as well where you can? Is that
Right now, these systems have not had insulated piping, and
okay?
that's one of the things that I feel should be done on it. And I think in the future, that's better. Now, they make the argument, well, the basement will stay warmer if you don't insulate the piping, which is true.
Yeah.
But now you're losing control of the energy to some degree.
Yeah.
So I would rather insulate the piping and control if we need more heat into the basement to warm it up, we can do that through a controlled heat emitter rather than just, yeah, the pipes will keep the basement warm.
Okay, this is a little bit long, but so these systems are extremely efficient, great for comfort, affordable to run on an operational month-to-month basis. But what is the ROI if, say, a full system cost is 2 to 3 times as much as a more traditional forced air system? Um,
It's a good question. And right now, I will say, without getting into specific numbers, these research systems are too expensive.
yeah,
That's telling the people I've been working with, some brilliant people that have been working on these projects, but they aren't necessarily, very familiar with the hydronics industry. And one of my first comments is it works quite well, but it's too expensive. It's far too expensive. We do see opportunities to value engineer the system, but I also want to look at when you can buy energy at a very low cost, and literally, imagine instead of 25 cents a kilowatt hour, you're buying this energy at 2 or 3 cents a kilowatt hour. When you look at total owning and operating costs, put those two together, you can make a good economic case for a significantly higher initial investment with a much lower operating cost.
right.
And quite honestly, I think the way these systems will likely go to market, there'll be a financing plan set up, similar
Mhm.
to how solar PV is marketed today. Many people, a $30,000 or $40,000 solar electric system on their house, they simply don't have the upfront money to do it. But with financing that's provided, you're basically going to look at what is that total monthly payment. And obviously, if the operating cost is very low, you can afford to go to a higher initial cost system. So it'll be marketed much like solar PV is marketed with
Yeah.
financing provided through a third party.
And you're showing these in existing homes that you said, I mean, could be potentially kind of leaky. They're not exactly
Mhm.
um, state of the art. So when it comes to eh, doing these applications as a retrofits or new construction, I mean, obviously they could be working both.
Absolutely. And
Yeah.
the size of the equipment, the size of the storage could definitely go down depending on what the load is.
Yeah.
And the cost of the system would be lower. So yeah, it would scale. It would potentially scale to a much more efficient building envelope.
Well, in talking about scale, I mean, people are asking about what's the minimum size for commercial applications. I mean, when it comes to the savings, the scale is that much more significant, the amount that you'll be saving with the larger.
Could be. You have to look at the rate structures.
Yeah.
Some utilities, I know our local utilities with commercial rates, you pay for both energy and you pay for demand charges.
Right.
Now, again, I think utilities faced with rapidly growing interest in electrification and literally scrambling to figure out how are we going to make our grid so that it can handle a much broader base of
Yeah.
customers or kilowatt hours. They're going to be looking at rate structures, and it could be as simple as if it's a time of use rate structure, the demand charge might be lower or it might be gone entirely. So again, I think utilities pretty much are being forced to look at what I'll call creative rate structures. And these projects that we're doing up in Maine are again proving that thermally the concept works. Now, how can we take this to entities like at least in New York State, it's the Public Service Commission. You can't just simply go in there and say, well, we think this will work. Here's data over
Right.
several heating systems or seasons rather that shows that these systems can work. So uh, it may be several years before these concepts come out in mass production, but we're That's why I'm very optimistic about hydronics technology in general. It is the glue that allows us to create what could be a whole new generation of systems involving thermal storage that can leverage these upcoming rate structures.
Yeah. Someone, this is going off topic a little, but would you set up domestic hot water indirect storage in a similar fashion as your tank battery on the bottom, or all parallel?
Uh,
Similar.
there's a lot of potential ways you could set it up. The
Yeah.
one slide that I showed, it basically is what we call a sidearm heat exchanger. It's basically a stainless steel braze plate heat exchanger on the side of one of the thermal storage tanks, and it simply pulls heat from the tank and transfers it to domestic hot water. You could set up an indirect tank, but one of the issues right now with indirect tanks in North American market, the coils that are in these tanks are pretty small relative to some of the tanks that are available in Europe. So we do want to be careful because remember, at times as you're discharging thermal storage, the water that you're supplying to your load, whether it's space heating or domestic water, that temperature keeps going down as you drain heat from storage. And to transfer the heat at the rate that you need it, you have to make sure your heat exchangers are large enough. Um, I tend to gravitate towards the braze plate heat exchangers because it's forced convection on both sides of the heat exchanger. You're pushing a lot more BTUs per square foot of heat exchange surface with a braze plate compared to a coil inside a tank. So I don't want to say it can't be done, but you're going to need a substantial coil surface area to allow that tank to operate at low water temperatures.
Um, in a slide that shows the three tanks piped in series, what is the advantage of having the connection of the last tank being horizontal rather than from the top of the tank? I
The advantage is you're injecting the water during the charging cycle. If you have hot water coming from the heat pump and you're injecting it into that right tank in the upper right corner, if you inject it vertically, and we've seen this with systems with pellet boilers, for example, when you inject into the top of the tank, you're literally creating a flow jet inside the tank, and it stirs the tank and basically destroys the stratification. So the concept is bring that hot water in gently and as slowly as practical, and don't create vertical currents inside the tank. Or I should say, minimize vertical currents inside the tank. So that's why that pipe comes into the tank horizontally. Now,
um,
you could create a tank, conceivably. I don't know where you find it on the market right now, that you could have a top connection, but have some type of a horizontal diffuser inside the tank. We've done that with pellet boiler systems where large ASME storage tanks, they actually have a top connection, but the water comes down and it impinges on a plate that's a few inches below that top connection, and that causes the water to basically change from vertical to horizontal flow and maintain stratification in the tank.
Okay, we're slowly moving from 30 mechanical minutes to 40 mechanical minutes.
I'm
I'm
good.
going to ask just a couple more questions and then we'll close out for today. But
Sure.
one person's asking, how does a designer correlate heat pump flow rates and minimum cycle times to buffer tank sizing so as to utilize stratification rather than mixing the whole buffer tank? Does that,
Wow.
is
That's
that,
that's it's a good question, but I can't give you a short answer on that.
yeah,
The best thing I can tell you is look at the tank, and if you're trying to maintain the stratification in the tank, horizontal flow, you might go to larger inlet sizes on the tank to slow the flow velocity down as it comes in. As far as sizing the buffer tank relative to the heat pump, is the heat pump an on-off unit where the compressor just turns on or turns off, or is it a modulating unit where you have variable capacity depending on compressor speed? As you get into modulating heat pumps, you can go to smaller buffer tanks. There are systems operating with buffer tanks that are 15 to maybe 30 gallons. That's it, because the heat pump itself will adjust its output rate as the load varies, as opposed to a heat pump that just turns on at whatever output it can, full output, that's where a buffer tank becomes larger and more necessary. But with variable speed compressors coming into this market very, very quickly, buffer tanks are going to get smaller.
Okay, that's interesting because someone is asking about the space requirements for such a system like you're
Mhm.
talking about. I mean, obviously more tanks, more space.
Absolutely. And in a house with a basement, these systems are practical. If it's a 1,000 square foot apartment,
Yeah.
it's not going to happen not with
Okay.
water-based storage.
Yeah, and so that's where again a couple of people have asked about the phase change materials instead of water. Um, is that reaching a state of commoditization?
Yeah.
Is it realistic or still science experiments? Um,
Yeah, I
yeah,
I wouldn't call it a science experiment. I don't
no,
think
it's
it's
proven.
really a commodity at this point either. It's
Right.
especially in the North American market. You mentioned SunAmp as one example of a product that has migrated from the European market over here. So we're at the initial market development with some of these phase change systems, but I do expect that market is going to grow.
Yeah. And I mean, you pointed to that example with the 290 using the R290, the
Hmm.
propane as a that was all over the ISH show in Germany. So in
Yep.
Europe, it's everywhere, but it won't be here in North America for a while yet. We're just getting
Well, yeah, we're going to
R32.
get there. I'm very
Yeah,
confident we are going to get there. In the States, I've heard speculation anywhere from 2 to 5 years. It basically
yeah,
has to go through UL, it has to go through ASHRAE. I believe it goes through EPA approval. It's going to be driven by global warming potential numbers. Propane is extremely low, and the politics of global warming potential is a huge incentive to drive. um, heat pumps towards propane-based refrigerant. And
right.
as you pointed out, Doug, there are literally tens of thousands of heat pumps running on R290 in the European and the Asian market at this point.
Right. Okay. I think we're going to have to cut it off there. I'm going to thank you again, John, for participating in today's 30 mechanical minutes or 40 as it went. Um, and of course, I mean, I look forward to seeing you this fall in September as we are bringing our Modern Hydronics Summit on September 16th to Calgary for the first time ever. And I know you'll be joining us. Looking forward to that day, a full day of in-person hydronics education, trade show. We'll have a lot of vendors there, a lot of good giveaways. I know that for sure. So we expect to see a lot of interest from the local plumbing community around Calgary and people from far and wide. So check out modernhydronicsummit.com for more information on that. And again, just thank you to everyone who joined us here today in 30 Mechanical Minutes. We had close to 300 people registered, so thank you once again for showing your interest in topics like this. It'll keep us doing it. And again, thank you to our sponsor, Lochinvar and Aquatech Sales and Marketing, for helping us to put this on for free, the 30 Mechanical Minutes for all of you out there. Just to let everyone know, a recording of this session will be available, so you'll be able to revisit those slides. And again, there's that article in the June issue of HPAC that talks about some of this, kind of the most simple, basic kind of system and some alternatives. You'll see it and you'll love it. Okay, that's about it. This will also be up on our YouTube channel before too long. That's at HPAC Mag on YouTube. You'll find us there. Subscribe today. Join the hundreds who are already there. That's about it. So until next time, thank you very much. Thanks again, John. Thanks, everybody. Goodbye.
Thank you.